All right, hello everyone, and welcome to the second lesson of Unit 8 for the AP Chemistry curriculum, which is on the pH and pOH of strong acids and bases. So I know in the first lesson we talked briefly about what constitutes a strong acid or a strong base, and that is 100% dissociation. Because strong acids and strong bases fully dissociate, we can use our initial concentrations to solve for the concentration of either hydroxide or hydronium. And with that concentration value, we can solve for the pH and or the pOH. So just a brief reminder about how to derive your strong bases and your strong acids from the periodic table. We know for our strong bases, they make a lowercase b on the periodic table, and then you just have to add your hydroxide to the end of those metals. Then with our strong acids, we have the 3 from the periodic table, Clobri, which would be HCl, HBr, and HI. And then we have the 4 strong acids from our little jingle, Clo, Clo, No, So, 3434. Just remember that sulfuric acid does need 2 hydrogens because sulfate has a -2 charge. So remember from our last lesson that pH measures how acidic a solution is based on the concentration of H plus or H3O plus ions. And pOH measures how basic a solution is based on the number of hydroxide ions. Both of these scales use logarithmic relationships, so the pH is equal to the negative log of the concentration of H plus ions, and pOH is equal to the negative log of hydroxide ions. Let's dive into our strong acids first. So molecules of a strong acid will completely ionize an aqueous solution to produce hydronium ions and typically an anion. Because of this, the concentration of H3O plus in a strong acid solution is equal to the initial concentration of the strong acid, and therefore the pH of the strong acid can easily be calculated using the equations from your data sheet. So let's look at some of our strong acids in the table below here. First up, we have hydrochloric acid, and we have our equilibrium equation to the right here. We can see that our hydrochloric acid breaks down into chloride ions and hydronium ions. And because it is a 1-to-1 ratio between HCl and H3O plus, and we also know that all the HCl turns into Cl minus and H3O plus, that means whatever our starting concentration is for HCl, we know our ending concentration is going to be similar, if not the same, for H3O plus. All right, so this first example says, what is the pH of a 0.05 molar HCl? So when we're talking about HCl, we know it's a strong acid, and that means when HCl comes into contact with water, it fully dissociates into its constituent ions, which would be H3O plus and Cl minus. Now what that means is if we are fully dissociating, that means if we start with 0.5 molar of HCl, it's a 1-to-1 ratio with our hydronium ion. So we're also going to have 0.5 molar of the hydronium ion. And it's very important that you note that this is only for strong acids and strong bases because they fully dissociate. With weak acids and weak bases, we have a different process to get those concentrations. So because it's a strong acid and we have 0.05 molar of our acid, we know we're going to have 0.05 molar of our hydronium ion. So now that we have that and we know that the concentration of hydronium is equal to 0.05, we can go ahead and get pH by taking the negative log of hydronium ions. And that equation is in your reference sheet. So doing that, negative log of 0.05 and that means we have a pH of 1.3. For our next example, it says, what is the pH of 2.5 times 10 to the negative fourth molar HBr? So HBr is another one of our strong acids. So when we take HBr and we mix it with water, it's going to fully dissociate into H3O plus and Br minus. So since this is a 1-to-1 ratio, we know that if we're starting with 2.5 times 10 to the negative fourth molar, we're also going to end with that same concentration of hydronium ions. So we know that the concentration of hydronium is going to be 2.5 times 10 to the negative fourth. And we know that pH is equal to the negative log of our hydronium ion concentration. So we take the negative log of 2.5 times 10 to the negative fourth. And that gives us a pH of 3.6. Now on the previous slide, we went from concentration to pH, and now we are going in the opposite direction from pH to concentration. So we are looking at the concentration of HClO4 if the pH is 4.25. So again, just going over why this occurs, if we were to mix HClO4 with water, because it's a strong acid, it's going to fully dissociate into ClO4 minus and H3O plus. Because this is a 1-to-1 ratio, we know if we can find the concentration of our hydronium ions, that's going to be the same concentration as HClO4, which is what we're solving for. So first, starting with pH, in order to get the concentration of hydronium ions, I need to take 10 to the negative pH. So I already have pH, so 10 to the negative 4.25 is going to give us 5.62 times 10 to the negative fifth, and that is going to be our concentration of hydronium ions. Remember at the start of this question, we said whatever our concentration of hydronium will be our concentration of HClO4. So now our final answer would be the concentration of HClO4 is equal to 5.62 times 10 to the negative fifth. All right, and now doing that again with sulfuric acid. It says, what is the concentration of sulfuric acid if the pH is 6.33? So again, if we want to look at the equation for that, if we mix H2SO4 with water, we're going to get HSO4 minus and H3O plus. Remember, whatever we get for here, because it's a 1-to-1 ratio, is going to be the same. So we're going to solve for this, which will give us this. So now we have pH. So in order to get concentration of hydronium ions, we're going to take 10 to the negative pH. So 10 to the negative 6.33. When we do that, we get 4.68 times 10 to the negative 7th, and we just solved for concentration of H3O plus, which is the same as the concentration of sulfuric acid. So that will be our final answer. All right, so now let's dive into strong bases. When dissolved in solution, strong bases completely dissociate to produce hydroxide ions, and because of that, the concentration of hydroxide ions in a strong base solution is equal to the initial concentration of the strong base. So the only key difference here between the acids and the bases is with our strong bases, there are some that have different ratios than a 1-to-1. So if you're looking at calcium hydroxide, strontium hydroxide, or barium hydroxide, you have to make sure that you're aware of the 2 coefficient in front of hydroxide when you're doing your calculations, or else you will be incorrect. All right, now let's practice some of these strong base questions in this table example. So first we have sodium hydroxide as our base, and we are starting out with 0.15 molar of NaOH. First step is to calculate the concentration of OH minus. When you have a strong base, remember it fully dissociates. So if we're starting out with 0.15 molar NaOH, we're ending with 0.15 molar hydroxide ions. So that's going to be the same number. To get POH, remember that's just going to be the negative log of your concentration of hydroxide ions. So we're just going to take the negative log of 0.15, and that is going to give us 0.82. And then to calculate pH, we're just going to take 14 minus the POH, and that's going to give us our pH. So 14 minus 0.82 is going to give us 13.18. And that is our pH, which makes sense because it's very basic, so it's going to be high on the pH scale. Then moving along to potassium hydroxide, we are starting with pH, so we're going to go backwards. So first step is getting POH by taking 14 and subtracting 11.51. So that is going to give us 2.49 for our pH. I'm sorry, POH. Now from there, we can get concentration of hydroxide ions by taking 10 to the negative POH. So plugging that into our calculator, we're going to take 10 to the negative 2.49. And that's going to give us 0.0032, or 3.2 times 10 to the negative third. Same thing. And then because we have a strong base, our concentration of base at the beginning is going to be the same as our concentration of hydroxide at the end. So we're going to have the same number here. All right, then moving down to calcium hydroxide. We are starting with the information of the concentration of hydroxide ions. And we know because it's a strong base, that's going to be the same as the concentration of base. So 9.4 times 10 to the negative fifth. To get our POH, we're going to take the negative log of that number, which will give us 4.03. And then to get pH, we're just going to take 14 minus the POH, and we will get 9.97. And then our barium hydroxide example, we are given POH. So to calculate pH, we're going to take 14 minus 5.32. That's going to give us 8.68 for our pH. Then to get concentration of hydroxide ions, we're going to take 10 to the negative POH. So 10 to the negative 5.32. That's going to give us 4.79 times 10 to the negative 6. And since we have concentration of hydroxide with the concentration of a strong base, that is going to be, again, the same. All right, now let's take a look at some College Board examples. This multiple choice question says, which of the following pairs of mathematical expressions can be used to correctly calculate the pH and POH of 0.0015 molar potassium hydroxide at 25 degrees Celsius? So since we are given a strong base, that means we're going to start off, at least I'm going to start off with calculating our POH. So calcium hydroxide fully dissociates, so it's going to be the same concentration of hydroxide ions. So if I want to get the POH, my POH is going to be the negative log of the concentration of hydroxide, which is going to be 0.0015. So that's my POH. If I look at my options, the only one I can cancel out right away is going to be D, because it takes 14 minus that, which would be incorrect. So now looking at pH, to solve for pH, remember it's going to be 14 minus the pOH. And because we just solved for pOH, it makes it nice and easy. So it'd be 14 minus what we solved for pOH, which was here. So negative log of 0.0015. So that would give us C as our answer. All right, and our last question for 8.2, which of the following statements about the pH of 0.01 molar HClO4 is correct? So HClO4 is a strong acid, which means it's going to fully dissociate and produce hydronium ions. And they are going to be a 1-to-1 ratio. So because we have 0.01 molar HClO4, that means we have 0.01 molar H3O+. So now looking at that, I can see that we are comparing pH values. So let's go ahead and solve for pH. And we know to get pH, that's going to be the negative log of the concentration of H3O+ or H+, whichever way you want to look at it. So now to do that, we're going to take the negative log of 0.01, and that's going to give us a pH of 2. So now looking at that, we know we can cancel out C and D, and we're looking at just A and B as answer choices. And it says, A says pH is equal to 2 because the concentration of H+ ions is 1 × 10⁻², which is correct.